Hey everyone, and welcome. You ever look at your phone, see it recognize a face in a photo, and just wonder, how does it do that? Well, today we're going to pull back the curtain and find out how machines actually see and make sense of the visual world.
Seriously, think about it. How does a machine, a bunch of code and circuits, look at this picture and know it's an apple? It's one of those questions that sounds super simple, but the answer is what unlocks the entire field of computer vision.
When we see an apple, our brain instantly processes its round shape, that bright red color, the little stem on top. But for an AI, it doesn't see an apple at all. It sees something totally different, a complex flow of data that all boils down to one simple thing: numbers. And that right there is the secret sauce. For a computer, this picture of an apple gets stripped of all its meaning and becomes a purely mathematical object, basically a giant grid of numbers. Let's break down exactly how that works. Okay, so to really get how AI works with images, we've got to start with the fundamental building block of any digital picture you've ever seen. You guessed it, the pixel. Think of it like a single tiny tile in a massive mosaic. Every single tile has a number that tells it what color or brightness to be, and when you put millions of these little numbered tiles together, boom, you get a complete image. This grid here, this is exactly what a computer sees. Not a picture, but a matrix of values. Each little p is a pixel with its own number. So when we talk about resolution, like say 32 by 32 pixels, we're just talking about the size of this grid. A 32 by 32 image has 1024 of these numbers for the AI to analyze. Now here's the thing. Not all pixels speak the same language. The way these numbers are organized really depends on whether we're looking at a full color image or just a simple black and white one. And the big difference here really comes down to complexity. See, with an RGB or a color image, you've got 3 separate numbers for every single pixel, one for red, one for green, and one for blue. But a grayscale image, it just needs one number for brightness. For an AI, less data usually means faster, more efficient training, which is a huge reason why grayscale is so popular. And here's a quick peek at how that RGB system works. Think of it like mixing paint. Each of those 3 channels can have a value from 0 up to 255. So if you crank the red channel all the way up to 255 and leave the others at 0, you get pure red. Max them all out, you get white. Turn them all off, you get black. Literally, every color you can imagine is just a different mix of these 3 numbers.
Okay, so an image is a grid of numbers. We've got that down. But you can't just throw that raw grid of numbers at a neural network and expect it to work. Nope. First, that image has to go through a kind of boot camp to get it whipped into the perfect shape for the AI to learn from, and we call this the pre-processing pipeline. This is our game plan. We're going to walk through these 4 essential steps that take a raw, kind of messy image and turn it into clean, standardized data that's perfectly ready for an AI model to actually learn from. First up, we usually simplify the image by ditching the color and converting it to grayscale. This move alone cuts the data down by 2/3, but we still keep all the important info about the shapes and textures. It uses this weighted average formula, so a single color pixel with values of, say, 120, 60, and 200 gets crunched down into one brightness value, around 94. All right, now let's get into 2 really crucial steps that are all about making our image data consistent: resizing and scaling. You see, neural networks are kind of picky. They demand that every single input image is the exact same size. So we have to resize everything to a standard, like 64 by 64 pixels. But wait, what happens if you try to make a tiny image bigger? You suddenly have a bunch of empty spots in your pixel grid. Interpolation is the clever math trick we use to fill in those gaps. The simplest way to do this is called nearest neighbor, and it's super straightforward. To figure out the value for a new, empty pixel, you just find the original pixel that it's closest to and copy its value. That's it. It's really fast, though sometimes it can make the final image look a bit blocky. And you can see it in action right here. On the left, we've got a tiny 2x2 image with just 4 pixel values: 10, 20, 30, and 40. On the right, we've blown it up to a 4x4. And look what happened. The original pixel values just got duplicated to fill in the new grid. The top left corner was a 10, so now that whole quadrant is filled with 10s.
Okay, next up is scaling, which you'll also hear called normalization. Here's the deal. Neural networks can get a bit unstable when they're trying to learn from big, varied numbers, like pixel values that go all the way from 0 to 255. So to help them out, we scale everything down into a nice, small, consistent range. It sounds simple, but this step can make a huge difference in the model's performance.
So here's our sample 3x3 grid of pixels before scaling. As you can see, the values are all over the map, right? We've got a 50, we've got a 220. This is exactly the kind of volatility we need to smooth out before we hand it over to our model.
The most common way to do this is with min-max scaling. It basically just squishes every value into a range between 0 and 1. The formula is actually pretty intuitive. For any given pixel, you just subtract the minimum value from the whole image and then divide by the total range.
And voila, here's the result. Our original grid is completely transformed. The smallest value, 50, is now 0, the largest value, 220, is now 1, and everything else is just a decimal somewhere in between. Now, this isn't the only way to do it. You can also scale things between -1 and +1, or use a method called z-score standardization. But they all have the same goal: make the data stable and much easier for the AI to learn from.
And that brings us to our final step, flattening. Why do we do this? Well, a standard neural network, a multi-layer perceptron, just can't read a 2D grid. It's not built for that. It's designed to take a simple, one-dimensional list of numbers as its input. So we have to unroll our 2D image grid into one long line. And it's exactly what it sounds like. We literally just take the first row of pixels, then we tack on the second row right after it, then the third, and so on until our entire grid has been turned into one very long 1D vector. Now, finally, it's in a format that the neural network can understand. And here it is, the entire journey in one single diagram. We start with our raw Apple image, convert it to grayscale, resize it, scale down its pixel values, and then flatten it into a vector, all before it even touches the neural network. This isn't just a nice to have. This whole pre-processing pipeline is the essential bridge that makes modern computer vision work. So at the end of the day, we've learned that for a machine, a beautiful image is really just structured data. By converting it, resizing it, scaling it, and flattening it, we get that data ready for an AI to find patterns that we could never spot on our own. And this powerful process is unlocking new discoveries every single day. The only question left is, what will it help us see next? Thanks for diving into this with me.